All right, let's do it. The final session. All right. Okay, so this is really meant as a proof of concept. Many of you out there in the interworld and in this room will be actually proficient with Python, and maybe you've done some machine learning. I'm a philosopher. I wanted to show you that these things were useful for something, so I learned Python to make this tutorial for you. So look, I mean, this code is going to be, it's going to be a stinker, but then just think of what like people with skill can do if we can. But in all seriousness, the team now will move on to working with some people in computer vision at Bristol to make this stuff a little bit more serious. But we certainly welcome your input about ways to do this in a way that's not, stuck in 1980. Okay, so let's get to it. I imagine there's a mix of people in here, some people that really have very little idea of how neural net classifiers work, and some people who have a pretty extensive experience. So I'm sorry for those of you that know this stuff well. I'm going to give you really bare bones, broad picture view of how they work, and then we're going to see it in action. So here's what we want to do. We're going to build a neural net that classifies images from the fashion MNIST data set. So this is a data set of 60,000 images. They're 28 by 28 grayscale images of items of clothing, and it's a labeled data set, and it's publicly available. And indeed, when you do the code, you'll probably be downloading the fashion MNIST data set if you don't already have it loaded. And here's the labeling system: 0 for a t-shirt, top, 1 for trouser, and so on down the list. And what we want to do is build a classifier that learns accurate sets of desirable gambles on this state space. So if it had to accept or reject gambles that pay out if it's a t-shirt or trousers or pullover or whatever, we're gonna train it to do that, and hopefully it's gonna do it accurately so that it's learning to, for example, accept gambles that pay out. You feed it a t-shirts, and then it says, yeah, I want gambles that pay out a lot on t-shirts, but not ones that pay out a lot, or not ones that lose me a lot on dress and coat and so on. We're going to build a quite simple neural net, a 3-layer neural net. It will have 28 by 28, so 784 input nodes. These are 28 by 28 grayscale images. So each of the nodes, when you give it a sample, each of the nodes will be a value between, sorry, I'm experiencing the same thing Hurt did when he plugged this into his computer. A value between 0 and 1 telling you how dark that pixel is. And then there's going to be a hidden layer, and in principle, we would have 10 output nodes. 1 for each of the classification labels. Ours is going to function a little bit differently because we're learning sets of desirable gambles, not learning classification probabilities. So our neural net will only have 2 output nodes, and I'll tell you why in a few minutes. But typically, we train this thing as if we extract probabilities from these final nodes. So how does that work? Well, you're going to feed it some input. Some are going to take higher values than others. So intent brightness here is sort of proxy for the grayscale image, and that's going to make the input nodes. There are going to be weights here. That's going to make the input nodes light up at different intensities. And then there are going to be more weights here, and that's going to make these light up at different intensities. And the values of those, we're going to extract probabilities from those. Let's walk through in slightly gory detail how all of that works. So you can think of these weights as living in a grid here. And when we feed it this image, we're going to have values for all of these. And then so then we're going to have weights that connect these to these. This is fully connected. In principle, you would arrange this thing more wisely. But these weights you can think of as living in a grid here. And how do we figure out how much the value of this node? Well, we're just going to take the value. Imagine that these are matched up, so they're both 28 by 28. We're going to take the value here and multiply it by the value here, and then the value here and multiply it by the value here and add those together. We're just going to keep going through all the way through, and you can see that you could do edge detection or something like that, even though that's not what our neural net will do. If you have, say, the weights be I don't know if you wanted to detect an edge over here. If you had it be high values here, so that it lit up when there were, like, you get big values by when you feed an image such that there's an edge here. And so they're intense. You have high weight values here, and so you're getting big sums when you do that. If you have negative values here, then those are only going to be zeroed out when the intensity stops next to it. So you can build weights that would, learn sets of weights that would do edge detection in that way. Really, our model is going to end up being overfit, so we're not going to do anything so fancy. And then we go through, we have different sets of weights for each of these, the lines connecting to this node, then we do the same for the next node, and we carry on and we determine values for the next node we carry on for each layer until we get output values. A little more formally, how is that going? Well, we're representing the input here as this little column matrix. We have these weights. In our case, we have it in a 3x5 matrix. And to get the value of the first one, we're just taking the input values, and then we have our 3 weights here, and we're just doing matrix multiplication. So that gives us the value for the first node. And then we do the same thing for the second node. We have weights connecting here, connecting the 3 input layers to here, and continue on. That gives us all the hidden variable values. So this is just linear algebra. It's not anything high powered. And then we're going to do the same thing at the end. We have more weights here. We're going to take the values of all the input nodes, do matrix multiplication. We get the value for y1, and we're going to do the same thing for y2. So pretty simple linear program. And the interesting stuff happens in training the net. So we're going to start out with a randomly distributed set of weights. And that's going to give us, we're going to feed it an image. That's going to give us values here, and we're going to extract probabilities from those 2 values. How are we going to do that? Well, there are different ways of doing this, but you could, for example, apply softmax. Softmax just takes these, turns them positive, and normalizes them. This typically, when people use cross entropy loss, they extract probabilities using softmax. Okay, so now we've transformed these 2 output values to probabilities, and then how are we going to score them? Well, we're going to use a scoring rule. In this case, we're going to use the log score cross entropy. And how does that work? Well, we just take the log. So we figure out, let's say it's whatever label 1 was, or label 0 was, t-shirt, I think. Then we're going to take the probability corresponding to that first label, the probability that it's a t-shirt, and we're just going to take negative log of that, and that's our penalty. And you don't get penalties in cross entropy. You don't get penalties for how you distribute probabilities. I'll put the false notes where if you were using something like mean square error, you would those would matter. Okay, and really, we're not going to do this for a single sample we're not going to train it each time on a single sample. We're going to give it a batch of samples, and then we're going to average the error that it gets for this sample, and for this sample, and for this sample, and this sample. So given a fixed batch, the error that we get is just a function of the weights. So you plug in some weights, there's a fixed batch that we're evaluating it with respect to those weights, determine the output probabilities, which then determine the loss. And now we know, okay, we've done yay poorly on this training batch. How do we improve things? Well, we're just going to look at the gradient of our loss function, and that's going to tell us how to nudge the weights in a way that improves things as quickly as possible. So what we're really doing here is wiggling each of the weights, seeing what effect it has on the loss at the end, and picking the combination of wiggles that makes us improve things as quickly as possible. And then we're going to do that over and over again on a few different training batches. So what does this mean? Well, the gradient, so if this is our loss function, the gradient at a point is a vector. I mean, we talked about the gradient before, but what's important for our purpose, so it's just the vector containing all the partial derivatives with respect to the weights. What's important for our purposes is that that vector points in the steepest direction of the loss function. And so that's going to tell us how to go uphill. If we want to go downhill as quickly as possible, we go in the opposite direction of the gradient. So all we need to do is figure out that gradient, and then we'll know which way to push the weights to improve things. And so we're going to adjust those weights by looking at the gradient, nudging it some epsilon in the direction of the gradient. And we're going to repeat that over and over and over again. And doing this will improve some of the weights more than others. And intuitively, the weights that are most important for determining the loss will get nudged around more than others. And this is not, determining this gradient is something that's not so hard to do, because most of this is they're just linear equations. The only thing, so we mentioned in yesterday's session we saw, and actually in the notebook, we're going to apply some functions on the weights in between ReLU and a sigmoid function. Those are just to kind of either get rid of the negative weights or take all the negative ones and make them positive. Either just zero out the negative ones and leave the positive ones as is. That's what ReLU does. And the sigmoid just takes all of them and kind of we'll click it. So negative, when you're out here, you get a value really close to 0, and then around here you start moving up toward 1, and then big values approach 1. This is bounded above 1, 0. So that's going to make calculating these gradients a little more annoying, but it's not bad. Okay, so how do we do it? Well, let's just do it with one sample. The only reason I'm walking through this is to give you, those of you that don't know this, it's a slight overview, but I want to highlight what's going to change, where it is potentially going to become more complicated when we put in IP scoring rules. Okay, so if I'm calculating let's say I pick a label. So again, I have a shirt and I want to know, well, how could I have nudged things in a way that would have improved, lowered my score as quickly as possible? Well, what is the loss? It's just negative, in this case, log of P1, which is a function of these two things. So if I plug in P1 there, this is the loss when these, as a function of these two output values. If I want to know how much nudging Y1 changes the loss, well, I just take the partial derivative of that thing. And that's the hardest step of this. I won't walk through it, but it's, taking this derivative is not particularly difficult. But it's the hardest thing. All the other steps as we go back are pretty straightforward. So if I then look at Y1 as a function of the values of the hidden layer and the weights going into Y1, that's just a linear function, and taking the partial derivative of that with respect to, say, the first node in the hidden layer is pretty easy. It's just this first weight, V11. And we do that again, we do that again going backwards, again, simple. And then if we want to know how much wiggling this one, or this first weight, weight 11, changes the loss, well, then we just apply the chain rule. It just involves taking the product of these partial derivatives that we just calculated, which were all pretty easy. So put it in, you get that. So maybe just to get you used to these loss functions and seeing how they work in action, let's build a loss function in one of our IPI notebooks using these torch commands. So I gave you the first step of this here. So here I'm building this term inside. What did I do to do this? I squared the output. So the output is our probability here. I squared this probability and I added it to the square of 1 minus this probability. So building this, we're going to build the spherical score now. That's what this is. Building this just involves applying these operations and nesting them inside of each other. So then I need to take the square roots of this thing, and then I need to figure out the absolute value of that, divide these two things, and then subtract, and I need to take the average of those two things. So if you open up the spherical with exercises notebook, why don't you have a go at that, putting that together and see if you can get it to run, just so we can then use that loss function to train a super simple neural nets to learn jump data. So I'll open that here. Was everybody able to successfully? Some people have Anaconda installed. If you open up Jupyter Notebook, or if you already have VS Code installed, on the SIPTA Summer School website, I have 2 sample Python notebooks, and pick the spherical one and just open it up.
It's not for it's not for download.
Not for download.
Yeah. But the rule for the rule
Right.
So if you have a Jupyter notebook open, we can see the first steps of this in action. So take 1 minute. So what we want to do is put that loss function right here, where it says define spherical loss. Much the right-hand side? Bigger? You can forget about the third. I don't care about mean. Mean does that for you. Did you get it?
No, we don't have yet.
Ah, yes. Yes.
Did you run the, try running them all?
I'm also black. Yeah, but that's the result.
Okay, so many of you are to the end of it, but not getting a plot. That's because the plot uses matplot at the end, and we won't have matplot installed. I'll show you what the plot looks like. If it's running and giving you an empty plot at the end, then you've probably done the code correctly. So let's walk through the notebook now. Sorry, I forgot that I put that down there, and then I didn't actually give you instructions to install matplot. But let's see what's going on with this. So the reason that we're doing this is because it's the first, it's our first sort of exposure to changing out the loss function in a neural net classifier. So let me walk through this step by step. What we're doing here is specifying the size of our neural net. So we're going to have 100 input parameters, 100 hidden parameters, 3 output parameters. We're going to train this. The batch size is just going to have 5 samples. Doesn't matter. And then I think we train it with a ton of epochs at the end. And the learning rate is just how much when we nudge, how much we're nudging. And what's the data here? Well, we are just randomly, we're just randomly generating a list. So this is going to be quite a big list. If I run this and then stop it, you'll see that these are what our inputs look like. They're just positive and negative numbers chosen randomly, 100 of them. And then we're choosing the weights randomly. And so what is the task in the end for this stupid neural net classifier? We're giving it these 5 sequences of 100 numbers, and we're training it to figure out which of the 5 it is, and it's going to do that just by overfitting. So we're not actually training it to learn anything interesting here, just learn which of the 5 stupid randomly generated things we've handed it. And let's see. I don't want it to print this anymore. If we look at what the Y data is, that's our target data. Sorry, those were the things that we were adjusting. Sorry, the things that we're trying to learn are yes, sorry. We have one of these 5 this is why you shouldn't have somebody who doesn't do machine learning to teach you anything. We're gonna label this thing. Yeah, let's go down to here and we'll see what's happening. So we feed it an input of 100 random numbers. It's gonna spit out.
Jason, sorry,
yeah.
can you increase the size of the list, please?
Yeah, sure. I think so. Yeah. Okay, good. And we'll see in the training what we're actually learning here. So what's happening when we train this thing? Well, we're feeding it 100 random numbers. So we've specified our neural net randomly, the weights in our neural net. We're feeding it 100 random numbers, and then it's going to spit out, because there are only 3 output values, probabilities for 0, 1, sorry, probabilities for it in being one of 3 categories. Now, we're just randomly labeling the things as belonging to one of the 3 categories, but we're trying to teach it whether this random set of numbers belong to this category or another category, or the 3rd category. So in the real case, we're not going to just have randomly generated strings of 100 numbers. They're going to be the pixel images of our fashion in this data set, and they're going to be labeled not randomly, but by a human who's just told us whether it's a shift or whatever. Okay, so that's what's going on here. And when we train it, we're going to use a loss function to train it, and now you have inputted the loss function, so let's check whether you've gotten that right or not. So does your output look a little bit like this? Have you used torch mean first to take the sum of the things, and then 1 minus the fraction, and use torch divide to generate that fraction? And then the numerator should be the absolute value of 1 minus the output minus the target, and the denominator should be the square root of the square of the probability plus the square of 1 minus the probability. Is that what everybody has? Okay, good. If you've done that, and you run this and you're getting a green check, then you've done it correctly. And now go ahead.
For the next step in the framework we put online, we set for epoch in range 1. So everyone who didn't get a figure is just because they only ran 1 time, so you have to almost 0.6.
Sorry, so go ahead and change that to big. And maybe if you have an F1 installed. What's that?
What are the big factors?
The range there has been set to something very low, but you might also not have map plot installed.
That doesn't know.
It's 5,000.
And so what have we done? Not much. We've randomly generated data. We've set up our neural net with an input layer, hidden layer, output layer, randomly generated weights. We've specified the loss function that we're going to use to store the classification probabilities that it gets at the end. And then we're going to train it by handing it batches, the same batch of data over and over and over again. And at each step, we're going to feed that data into our neural net. It's going to do some linear algebra. It's going to make, we're going to output classification probabilities, and then now we're using the spherical loss that you just defined to penalize it, depending on how close it was to getting it right. And then this step here is calculating the gradient, the backward step. So by using the tensor, the torch operations, we've done these operations in a way where Python is storing the computational graph. It's telling you what it can take partial derivatives with respect to. When you try to do this for IP loss functions, that's the hardest part of getting it to just build the graph in the right way so that you can take the relevant partial derivatives. But once you can do that, once you have the computational graph, then it's just calculating the gradients and then
after each training session, it's zeroing that out so that it can redo the gradient for the new batch. And once you do that over and over and over again, you see that it looks something like this. The loss is going down steadily over time, but it's not doing anything interesting, right? I mean, it's not picking up any interesting patterns. We're just feeding it the same data over and over again. Eventually it's learning to identify a specific sample. It's not learning to generalize in any way. So now let's do this. We're just going to do this in a slightly more complicated way with IP scoring rules rather than the spherical score. And we're going to try to get it to learn a little more sensibly than what this thing is doing. So before we do that, let's go back and let me just highlight. Let me just highlight some things that change when we use IP scoring rules, because there's a little bit of a shift of perspective that one needs to use to employ these things in neural net classification. First, I'm going to cull this data set so that we're only looking at 3 categories. This means we're looking at sets of desirable gambles with a sample space of 3. We could do it for higher than that. It would just take longer to run, and it wouldn't be insightful. So we're just going to look at t-shirts, trousers, and pullovers. And we're going to do this with a particular 2-parameter scoring rule, one that I mentioned earlier, where the penalty function is just a particular constant scaling. So the type 1 error is here. Lambda tells us the type 1 error. So you give me a gamble. Let's say the gamble is 1 to -3. And this is in my set of desirable gambles. It turns out I have some bad luck, and we're in world 3, and I lose 3 utils. I've misclassified this gamble. I've committed a type 1 error. I said it's desirable when it's not. What is my penalty for that? In this case, it's just -3 lambda. So this lambda is telling me how important it is to avoid type 1 errors. Actually, the penalty is the negative of this, so I get a 3 lambda penalty. And if I was in world 1 or world 2, then I would get a 2 gamma penalty. Okay, so we're just scaling. If I am silent about this gamble and it's a good world, I get a penalty that's proportional to the amount of utility that I left on the table. If I'm in a bad world, and I say it's desirable, I get a penalty that's proportional to the amounts of utility that I incur by accepting this gamble. And because, oh, go ahead.
Why do you lambda should be larger equal and
Yeah, so this is part of one of the axioms that we didn't discuss. But there's a kind of, the axiom 4 was a superadditivity axiom. And it's a kind of conservativity axiom that says avoiding type 1 error always has to be at least as important as avoiding type 2. If type 2 error were more important than avoiding type 1 error, then you'd start accepting gambles X and not X. Because it's more important to get the one right than it is to avoid the one that's wrong, and then you would start being incoherent. So we can't have that. I mean, what I take away from this is that there's a kind of preference for type 1 error, a kind of conservativity in that sense, built into our notion of coherence. Okay, so this is the simplest way you can do this. And for this special class of scoring rules, we can take that dominance result that I gestured at briefly, and we can actually specify the class of
sets of desirable gambles that are non-dominated with respect to this simple 2-parameter scoring rule. So if you go to this link, I know it's a little bit annoying to actually type that in. I have a little visualizer for you so you can take a second to look at this class of sets of desirable gambles. It's parameterized just by these two positive constants, alpha and beta. So as you play with those, you'll get different boundaries of sets of desirable gambles that are in this admissible class, the class of sets of desirable gambles that are non-dominated relative to our scoring. So why don't you take a second to just explore that, type that in, just to get a feel for what the sets of desirable gambles look like. Yes, sorry.
Okay, so. I just copy paste it.
You need to sign in. Is that happening for everybody? No.
Yeah, me too.
But then so when I.
Maybe if there's somebody near you that.
Maybe it's like, maybe you have to sign in if you.
Yeah. LNG are these limited gambles. They allow you to change the story. Is it not working for you?
This is not Jason. Nice, now it's.
So these are boundaries. I have a set of desirable gambles.
So the big one, yeah, so it's maybe it's
Yeah, so you said.
Thank you.
maybe try to you have the link. So this might be the same because I also have the same problem with the link. It's everything.
It's a Creole set.
Which are
Yeah, there is a it's just it's these types of sets of desirable examples that are simple to recognize. Okay. So, I mean, obviously this shouldn't look particularly intuitive to you. It is a set of desirable gambles that is specified by the intersection of 6 half spaces. So there are 6 extreme points. They're given to you by upper and lower bounds, certain upper and lower bounds on conditional probabilities. We're not going to get into the details of that. The point here just is, as we make lambda greater compared to gamma, we're increasing the amount by which type 1 error matters, and that's going to make our models more conservative. They're going to be closer to vacuous. In the extreme, we can get the ideal. So, for example, if we pump A up as much as possible and pump B down as much as possible, if we didn't have these artificial bounds on how high we were letting A and B go, we'd be able to, as close as we want, to approximate the ideal in world 1, that half space. As you pump B up to infinity and A down to 0, you get the ideal set in world 2. And as you put A and B to 0, you get the ideal in world 3, just all the things that have the half space with everything with a positive z coordinates desirable. So you can go between those 3 extremes, and what the things in between look like, how close they are to vacuous, will depend on this lambda and gamma parameter. The bigger lambda is compared to gamma, the more imprecise it will be. The closer they are to equal, the more precise the intermediate ones will be. And so what you're seeing is, based on how conservative the scoring rule is, it will take more and more evidence that's pushing you closer and closer to certain to wash out imprecision, to push you closer to precision, according to, in this class of scoring rules. And
gamma equals lambda, is it that they are neutral?
If they're equal, then we get precise scoring rules back. So lambda and gamma were telling us they were parameters of our scoring rule.
You said they show how conservative we are.
Yeah, how much intuitively, how much more important it is to avoid making false judgments of desirability rather than staying silent about true.
When they are equal, means that we care as much
About one as the other, yeah.
which means they are neutral.
I mean, it means we're fully precise in this context, yeah. I mean, treating them equally is a kind of extreme, I think.
So you're very conservative in when we take them to be equal.
If we're very conservative, then we take lambda to be much bigger than gamma. And to be much bigger than gamma, yeah. Okay, and I wanted to show you this because, not because it's particularly important to play with visualizers, but once you fix lambda and gamma, you get all the things in the class that are non-dominated just by moving around A and B, or alpha and beta. And so what we're going to train our neural net to do is learn the correct values of alpha and beta, or A and B here. So, yes, I'm going to go back to that now. So
here, this is a big class of sets of desirable gambles. They are all the ones that are non-dominated relative to our scoring rule. And any alpha and beta that we pick will give us something in this class. So there's, continuum many things in this class. But depending on which ones we pick, we'll get things that are more accurate in some worlds, less accurate in others. We want to train it to be learn sets of desirable gambles that are as accurate as possible. Okay, so that's one shift in perspective that we're going to take when we're using IP scoring rules for this kind of classification task. Now, the alpha and beta that are in the output parameters, we're not treating them as classification probabilities that we're scoring directly. Rather, we're treating them as parameters of a set of desirable gambles, and then we're going to feed this thing into our IP scoring rule to determine the loss. And I mean, one slight complication as opposed to the simple cross entropy scoring rule. Now, when I wiggle something down there, it's going to, because our loss is going to depend, where we have to give it both parameters to specify the set of desirable gambles, and we have to give it the whole set of desirable gambles to specify the loss. Now, wiggling something down there is going to affect things through lots of routes. So when we apply the chain rule, we're going to have to do it more times, but it's not, none of that is particularly complicated. It's just doing linear algebra a bunch more times and then summing these things. So that part doesn't make it much more complicated. The part that makes it more complicated is this first thing that appears in the chain rule, the partial derivative of the loss function, which before was a simple loss function, something like the log score or the spherical score. Now it's this messy integral functional. And that is going to take, that's going to take a little more computational power to calculate the, sorry, I thought there was a question. That's going to be a little bit harder to compute, and so this thing is going to run much less quickly, and will take smart people like you to figure out how to do this more efficiently than I can. And the final thing that I want to note, and then we'll go through the actual use of IP scoring rules, is that you might be wondering where the classification is. It doesn't seem like these things are actually classifying. They're learning sets of desirable gambles, but they're not actually telling us whether it's a shirt or trousers or anything. So if we want to actually do the classification and check the proportion of things that it's getting right or wrong, we're going to need to treat that as a decision problem that we can use our set of desirable gambles to address. So we're going to have to specify gambles associated with classifying the image as a t-shirt, as trousers, as a pullover, and then if we're choosing between classifying it one way or another, accepting one gamble or another, we put these things, if these are our options, we can classify it as t-shirt, trouser, pullover. Then we're going to look at our set of desirable gambles. We're going to ask whether, should I kick t-shirt out of the set? Well, is there something else that is preferable to classifying it as a t-shirt according to my set of desirable gambles? There is, just in case, there is some V that I prefer to that, just in case the difference is in my set of desirable gambles. So if I have enough information, I'll narrow this down to a single gamble. I'll reject the other stuff, but sometimes I may end up, as we saw yesterday, delivering back a choice set that doesn't contain a singleton. It might just not have enough information to say, oh, this is a t-shirt, and this is these are trousers. Maybe that's a good thing. In any case, let's see this in action. So I'm going to go back to Visual Studio Code now, and we're going to start on this, just working our way down. and explaining what we're doing as we're going along so that you have a sense of how it's working under the hood and can do something better, hopefully. So what we're going to start by doing is specifying how to make this special boundary of the set of desirable gambles that we're trying to optimize, trying to learn the parameters of. So we're going to feed it this lambda and gamma parameters from our scoring rule, and we're also going to feed it this alpha and beta. And once it has that information, then that big conditional statement where it said, well, the boundary is this half plane if you're in this region, this half plane if you're in this region, this half plane if you're in this region. We're going to have to just code that in by hand. So that's what we've done here. There's nothing interesting going on. That is just this coded using torch operations so that we can keep track of the gradients. So now we've taught it how to build the boundary, and we need to figure out how we're going to do our integration since the loss function is an integral. So we have to choose a method for doing an integration. Here I'm choosing to approximate the integral by doing using Monte Carlo, stochastic Monte Carlo. So it's going to do a bit of a walk and then hopefully yield a reasonable. I mean, I think for what it's worth, for torch plot, Monte Carlo seems to be pretty good at approximating things better than some of the other methods. So now we've said how we're going to calculate the integrals. Now we have to tell it what the scoring rule looks like, which integrals to calculate. So we're going to make our penalty function in world one. We're doing this in, more or less exactly the same way that you just constructed the spherical scoring rule. So we've done that now. That's the penalty, that's the phi that we're integrating over. And now I'm going to teach it to actually do the integral when I feed it a boundary, a set of desirable gambles. And now let's test to make sure that everything's working. If it's working, when I run this, the value, well, is not working. Good for you. Well, good, that's what we should have. Oh, okay, got a number now. Okay, so what number did we get? 7.3696 in this case, not too far off of 7.48. We could increase the precision of our integrator. That's going to cost us more time on the back end. Of course, I'm sure you can, again, do this all better. So what have we done here to test this? I have made a set of desirable gambles. We taught it how to do that before. I gave it values of alpha and beta equal to 1. And the parameters of our scoring rule were, in this case, gamma is 1 and lambda is 2. And then I told it how to make the loss function that we want to integrate. And then I fed it that test set of desirable gambles and just printed that. And you can tell that things have gone okay for us because it is giving us a gradient that it's keeping track of. So we haven't broken the computational graph yet, which is okay. Now we're going to do the same thing in world 2, and I'm going to ask you to test it to make sure it's working correctly. So if you have this up, be running these things, make sure you're getting green check marks as we're going along. And now we're here, we want to make sure that our loss function at world 2 is working correctly. So if you could just copy and paste this, it'll allow you to, well, let's do it. If we go down to world 2, you can pick whatever value for alpha and beta you like. You can pick whatever values for lambda and gamma you like, and it'll give you the value that that set of desirable gambles, the ones specified by alpha and beta, the loss that it should get in world 2, according to our scoring rule. Then you go back to VS Code or Jupyter and see if the thing that we defined in there is giving back an answer pretty close to what you expect from here. All right? Just test it out and let me know if it's working for you.
Yeah.
Oh, yeah.
Yeah.
So think of it like on an analogy. Two parameters. Here, alpha and beta are just parameters. Run any meeting on their own. So where were you? Okay, so does anybody want to toss out some values for me and I can see if I can get it to work?
So what alpha and beta do you want to put in? Somebody help me.
7.12.
7.5.
Oh, under 7, just put 7.
7512.
Yes.
Okay, and what am I doing for tests?
Make IP loss 1, 2.
Make IP loss 2,
Yeah.
and then 1, 2. And what am I doing for test 2B?
Test 2A of
Test 2A of make, sorry, gamble.
Yeah.
Go, and what's my expected result?
So 6.79857.
Okay, let's do that. What do we get? All right, not so bad. Bouncing around kind of close. Okay, good. And we're gonna do this again for world 3. Define our world 3 loss function. And we don't need to do another test here. Okay, so now we've separately specified the loss that you get in world 1, the loss that you get in world 2, the loss that you get in world 3, when you feed it a particular set of desirable gambles, which is again parameterized by this alpha and beta. I mentioned this over here. Think of this like any parametric family of distributions. So if you take beta distributions, they have 2 parameters, fully fixes the distribution. Same kind of thing is happening here, maybe a less interesting class of sets of desirable gambles or models, but in any case, you fix the 2 parameters and you get back something in that class, a set of desirable gambles in that class. And now we want to tell it how to pick which scoring rule to use to penalize the set of desirable gambles based on which label comes up in our in the target. So we wanted, if you feed a t-shirt and that's label 0, we wanted to pick out the first scoring rule. If you feed it another one, whatever was 2 trousers, or whatever was label 1, we wanted to pick the second scoring rule, and so on. So we're going to do that here in a very flat-footed way. We're going to build a class of loss functions. This parameterizes it by feeding it the gamma and lambda value, and then we're going to call one of those things from, we're just going to make a list of these 3 scoring rules, and we're going to call back a function depending on what value the target takes. And then the loss that we're going to return is going to be the loss of the set of desirable gambles that are specified by this alpha and beta, given the right loss function to use at that world. So use the target, use the image to pick the right loss function, use alpha and beta to build the set of desirable gambles, feed that to the loss function, you get a loss. And that's the thing that we're going to try to reduce over time. Okay, maybe we'll skip this test here. But if we put in, say, I don't know, if any of you have the test value thing up still, let's say we put in 2 and 5 here, and let's say 12 and 1.7, and let's now see, this is telling us the set of desirable gambles, this is telling us the loss function to use. Let's see, oh, I've screwed this up. Oh, I didn't run this, did I? I never actually built the class, sorry. Probably do that. And now when we run this, we get some penalties. Do those cohere roughly with the test values that you're seeing? Let's see. So what did we have? let's just do world 1, loss function 2, 5, 12, 1.7. All right, so that looks, did I do that correctly? That gave us 0.83, and here we got something much closer to 0, but I guess.
Is this determine the 5 by the other way around? Yes.
So the 2 and the 5, I think, are in the right order because we're giving it gamma first.
Are they the same as what you put in?
But the gamma is 2 and this is 5. That should be okay. The A was 12, the B was 1.7. That should also be okay. This might just be an area where we're not getting enough precision out of this unless somebody else sees a mistake here. In any case, I mean, this one is low, so is this one. Not as low as we wanted, so maybe we need to up precision, but okay, so once we have that, then we can train our neural nets. And we're going to use the fashion MNIST data set here. Then this first part, I'm just restricting the training set to only include 3 items of clothing. And then here we downloaded the training data and downloaded the test data. So now we're going to train it on different data, then we're going to test it on so that it's not just, yeah.
I think last function you square A and B, I think that's what it means.
Yeah, we should.
If you where you define IP loss function, you square A and B. I think that's why I get different answers from.
Oh, that's right. So those should be squared there, shouldn't they? Yeah. Okay, good. Okay, and now all we're doing is setting the batch training sizes. We're going to actually be using an evaluation training sizes. We're keeping these low just because this takes a long time to run. This is not an interesting bit. Now we're going to have to build our neural nets. This is just what we were talking about before. The input layer is 28 by 28. And we're going to have 512 hidden nodes in the hidden layer, and 2 output nodes. Those are our alpha and beta. So that tells us what the set of desirable gambles look like. We're applying ReLU in between because who knows? If somebody actually knows why ReLU is so effective, please tell me. So again, ReLU, I mentioned this earlier, just zeroes out negative stuff and gives you back y equals x. So just returns the original thing. If it's positive, this makes the thing nonlinear, which I guess is nice, but I don't have a good explanation for you of why ReLU is so effective. Okay, now we want to choose our IP loss function. Is there anything in particular here that you are interested in seeing? Do you want it to be more conservative, less conservative? Give us more imprecise sets of desirable gambles or less? More? Yeah, more imprecision. So let's do, I don't know, 210. I failed to define this thing. Okay, so now it's pretty imprecise. And this is the thing that tells us how to actually train it. This is, well, these two sections are undoubtedly the hackiest part of this, so please forgive me. But all we're doing here is, when we're training, we're trying to put together, I'm using a little bit of a hack here to make sure that our data stays paired with the target in a way that doesn't break the computational graph, so that we can keep computing gradients as we go through. That's not particularly interesting though. There's nothing in principle different from what we were doing before, where we've now got this IP scoring rule in there. We've done it in a way where we can calculate gradients that lets us nudge the weights of our thing around in a way that minimizes, it pushes down loss over time. I'm not going to rerun this here because it's not interesting to watch, but you can see that the average IP loss is going down over time, although maybe not as quickly as you'd like. Maybe it doesn't have particularly nice properties. The last thing I'd like you to do before we call it for the day is run those previous things. Don't run the epic here, because that is going to tie up your computer for a while. Just run this final node, and I want you to, it should only take a few minutes. I want you, you can even stop it after. Is everything all right? You know, if it's taking too long to run, just stop it after a minute. I want you to let it run and then take the last two outputs and tell me whether you think they're sensible. Try to extract them, look at what set of desirable gambles it has predicted for the sample, look at what the sample value is, and see whether or not you think it's done a reasonable job producing an accurate set of desirable gambles. Okay, but I mean, it does have some.
That was just
Oh, is it?
all this.
Okay. Okay. Well, I mean, you can still test that for that. We just they just need to because it's very hard to I mean, surely there's something smarter than this. But absolutely right. I don't know. I mean, but did it actually oh, sorry.
Oh, no, that is way out there.
Yeah. But it's well, it's right. Just looking at the last two. Yeah. I mean, that's part of the exercise. I want to know whether, like, if you go with those, look at the set of desirable gambles. Yeah, and then compare some of the target.
Okay, so let's just examine one of these and see whether you like it or not. So here on this final sample, or these final two samples, we had, let's see. Where's my cursor? Let's see. About 69 for A. Too big. And what was the second value? It was, we square this. And then what values did we pick again for landing? Oh, this was done with just 1, 2, I think, originally. So, doesn't matter. And then the target was 0. So that means it's a t-shirt, that's world 1. And what did we end up with? We ended up with something that was, I mean, the kind of bad visualization of the boundary, but it's pretty close to the ideal set of desirable gambles at world 1. So at this point, we're not really getting the benefits of imprecision, just like an overfit normal neural net classifier. It's basically certain about everything. So we will have to do something much more clever to actually eke some value out of teaching neural net classifiers to use imprecise probabilities. But the applications do seem to me interesting. I mean, it seems like we could, there are lots of situations in which the data is incomplete or of poor quality or something where we intuitively might want our classifiers to be doing something like learning imprecise sets of desirable gambles. I won't opine on that anymore since that's not particularly interesting. So we'll leave it here. I know this hasn't been the, I don't know, maybe the most thrilling exercise, but I wanted to show you that you could do something with these things and that they help you, they might help push IP into areas that it hasn't been as prevalent. So, and there, after the coffee break, we will have a panel. Oh, go ahead.
Just for presentation, I would say. Problem. Okay. There's usually a problem and limitation with filtering is that we usually don't have a very open, let's say, you don't exactly know what is happening inside the network. So even if we say probability, usually want to have a big, let's say, be a bit more avoid. Let's say, you see what I mean? It's a problem with precise probability to avoid not having certain values, and then using the deep learning, it's a bit difficult to control them, to understand how they work. Could that be a problem? Okay, sorry.
No, it's okay. I don't think this is going to
And it's certainly not going to solve, it's not going to make deep nets any more transparent. But I don't know. I mean, I'd like to open this up to the room. It doesn't seem to me that it adds to the problem, that it would make them less transparent. It would just be incentivizing them to, in some dark magic way, do something with imprecise probabilities rather than precise ones. But do any of you see ways in which this might be, I don't know, exacerbate current problems bugging people in deep learning? Okay, well, maybe that's a kind of thing that we can think about and talk about in the panel discussion.